Okay, looks like everything's good. Okay, so here's where we left off last time. We were talking about this theorem right here. That basically there's a certain amount of setup that goes into it. But if you have a list of two vectors in R2, from that list you can make a matrix and a linear transformation, and thereby then also a parallelogram. And that all just is a matter of manually constructing them per this very regular procedure. The theorem comes in talking about how these things relate to each other. So in particular, the magnitude of the determinant is telling you about the area of the parallelogram, and the sign of the determinant, well, this is a bigger story here, right? But the sign of the determinant to a large degree is just telling you the order of the original list, whether it's counterclockwise or clockwise or neither, depending on whether the determinant's positive, negative, or zero. Okay, and then don't forget I gave you this other interpretation of the sign of the determinant. You can also think of that in terms of whether or not the linear transformation, and what the linear transformation is doing to the plane, is it, among many other things, rotating and stretching, etc., but is it flipping it over, right, mirror imaging it through some line, amongst other things, or not, right? So is counterclockwise preserved as counterclockwise or not, right? And so I like having the second interpretation. This interpretation here about whether the list is counterclockwise or clockwise is what I'm going to call kind of static. I mean, these image vectors are list vectors. They just kind of sit there, right? What's cool about this as a statement about the linear transformation is that it's kind of, if you will, not static. There's something happening here. The linear transformation is doing something, right? And in certain situations, that's actually really useful. So important to understand that from both points of view. Okay, so this again is what we talked about last time. Now we're going to move on and talk about the three-dimensional version of this theorem, and here's the good news. It's the same. I mean, not exactly the same. It's three-dimensional instead of two-dimensional, but it's so close to the same that if you were to guess, if you were to take this theorem here and just speculate, wild guess, you'd probably guess we'd be talking about three vectors in R3 instead of two vectors in R2. It seems like a reasonable guess, right? And that would make a 3x3 matrix, and those images would give you three edge vectors, thus making a parallelepiped, as you see here, right? So, again, as you would guess, three vectors in R3 makes a matrix, which in the usual way makes a transformation, which in this case makes a parallelepiped. And again, the results also exactly what you would expect by analogy. In particular, magnitude tells you how big is this image thing. Now it's three-dimensional, so how big means volume. Previously we were talking about two dimensions, how big means area. But still, volume instead of area, exactly what you would expect. And then likewise, the sign of the determinant is going to tell you this story, and again, you can view it in different ways. You can view this sign of the determinant as a statement about whether the original list is a right-handed list or a left-handed list. And again, that's kind of a static way of thinking about it, that the vectors just sit there, right? Or you can view it as a statement, oh gosh, if I can find my eraser, here we go. You can view it as a statement about the linear transformation, sort of a statement about something happening. And this linear transformation, if you think about it, x, y, z being as it is always right-handed, if the images were also right-handed, then right-handed turns into right-handed, which means that, there are rotations and magnifications and shears and things like that, but there's no mirror imaging because a right hand turned into a right hand, right? Whereas on the other hand, sorry for the pun, if the E1, I know it was bad. E1, E2, E3, if that turns into 3 image vectors like this that are a left-handed list, what has to be involved? If a right hand turns into a left hand, somewhere along the line, amongst the magnifications and rotations and things like that, there's going to have to be a mirror image in there somewhere, right? And so, again, you can view determinant's sign as a statement about the list of vectors. You can also view it, and arguably more importantly, you can view it as a statement about whether the transformation has an inversion, a mirror imaging somewhere in it. Okay, all right, you buy it? Does it seem reasonable? Do y'all see the analogy between this 3-dimensional theorem and this 2-dimensional theorem? Again, really, really similar. Totally analogous. Everybody happy? Okay. All right. Okay. So moving along. So now that we've talked about order, right hand versus left hand, and we've talked about determinant, on now to discussing cross product. It's a formula. This thing called the cross product is computed by that formula, and you can just leave it at that. I suppose that is the formula. Fine. Problem though, this is a weird formula, not immediately clear where it comes from, and if you were to just memorize this rote, I think you're eventually going to forget, right? I know I certainly would. So I don't recommend that you memorize that formula. I encourage you instead to think about this formula right here. This is what I like to call a symbolic determinant. Just to be fair, if you take a determinant, you're supposed to take the determinant of a matrix. If you have a matrix, the elements in the matrix are supposed to be numbers, but notice up here I have standard basis vectors where numbers are supposed to be. That's a square peg round hole kind of situation. You're not really supposed to do that. It's questionable whether you should even call this a matrix, and can you take the determinant of something is not clearly a matrix. So if you ignore all of that, right, just let the sloppiness go, compute the determinant symbolically. In other words, how would we take a determinant here? Well, we'd multiply that thing times the determinant of this minor. Oh, and notice that gives you that first coordinate up there just like that. Right? And then next you'd proceed and you'd take this times the determinant of its minor. That gives you this. Don't forget your minus sign there, by the way. Plus, minus, plus, and all that. And then on to the third term. So notice that just kind of blindly following the rules in a purely symbolic manner reproduces that formula that now you don't have to memorize because this is a little shortcut. Everybody okay with that? Yeah.
So if you're doing this, you have to use E1, E2, E3. You have to use that row. You can't basically like take out A1 because in other determinants there's like a row of zeros or something.
Let me say this: if you arrange things like this, then it works. There are probably other ways that you could arrange it that would also work, but I'm not clear on what you'd benefit out of that. So I don't want to say that no other arrangement works, right? But this one definitely does, and it is going to be hard to beat for convenience. So I'm going to suggest you always do it this way. That's certainly I always do that. Yeah, but yeah, totally. Yes.
I think what she said.
Yeah.
If you make the standard basis like 1, like a scalar of 1 instead.
Yeah, because then it gives you a totally different thing, and a lot of students do ask that question. So let's just consider hypothetically if we. What I'm going to do, I'm going to let's kind of erase that. Yeah. Okay. Cool. Close enough. And let's just put a bunch of 1s here. Right. And the problem is those 1s now are scalars. Kind of good news in the sense that now at least we feel like this is a matrix again, and it makes us feel better in a way. But notice the determinant of a matrix, of an actual matrix, it's a scalar. And that makes for a totally different critter. Notice this cross product that I've defined here is a vector, right? And so this is kind of doomed from the start. There's no way that could work because it produces not only the wrong result, but the wrong kind of object. Does that make sense? Kind of?
Yeah.
Okay. Okay. So yeah, tempting, but doesn't work. These do need to be standard basis vectors, specifically the 3 standard basis vectors in that order. Yes.
Is there any other way to take the mutual cross product of multiple vectors?
Per the exercise in the book, there is a generalization of the cross product in higher dimensions, right? But that is appropriate to the dimension. In 3 dimensions, this is the only cross product. And in fact, if you look at that formula in that book exercise and let n equals 3, you'll get exactly this formula. So if you want to cross more than 2 vectors, you need more than 3 dimensions. So for what we're going to be doing in this class, other than that one homework exercise, everything's going to be 3-dimensional. Yeah. Okay. Yep.
So that's D1, 2, 3, it's like IJK?
Yes, that's right. That's right. Yep. Yep. Everybody good? Yeah.
The reason you don't use IJK?
Yeah, because eventually you run out of letters, and unless you have a strictly I will not go over 3 dimensions under any I will not go over 3 dimensions under any circumstances. Then you start to run out of letters, right? And you remember that econ example that I showed first day of class, right? We needed 6 variables there. And so I guess that could be IJKLMN, but you can see it's going to get silly, right? And it's a nice, easy pattern to just call them this E notation. Yeah. All right. Cool. Formula. So here's another cool formula. This is called a triple product. You can see right here. I wanted to be in the highlighter mode here. Triple product. A triple product is defined by this formula right here. So it's a dot product with a cross product. So you can just write that down. I mean, let's see here. I mean, after all, dotting with some vector C. All right, there I go. Dotting with a vector C. The cross product. Okay, well, here's the cross product. And so I can just multiply this out, right? Just multiply out this literal dot product. And here's what you notice. The first term of that dot product is that times that, which then you come over here and you notice, well, that's this number times the determinant of this 2x2 submatrix, starting to look like this is actually determinant. And in fact, if you write down all 3 of the terms, let's see here. Let me use the dark blue here. This times that, you'll notice, is that times all of this. Don't forget your minus sign. Plus, minus, plus, and all that. And then likewise for the third term. And so, sure enough, the pieces just all fit together. And what we have then, whoa, I didn't mean, oh my gosh, what's going on here? Sorry, computer technical difficulties. Altogether, what we have is that this thing called the triple product is literally a determinant. This is not a symbolic determinant, forgive the sloppiness kind of deal. This is literally a determinant. This is literally a matrix. It is exactly the same as that triple product. Yes?
Would it be different if you did A cross B and then dot product with C?
I hear you. So I'm going to say yes and no. I'm going to say there's a landmine there. Now, just by the commutativity of dot products, it is true that you can write this as A cross B dot C. But what we're going to find in a minute is that we're going to be taking these 3 vectors and kind of cycling through them. And the order that these things are written down in is going to matter. And so while, yes, of course, dot products are symmetric, and so you can do this, I'm going to suggest that you never do, because I feel like it'll introduce confusion where there otherwise wouldn't be, and it's another one of these, whether you could or not doesn't mean that there's anything to be gained from it, but I think there's confusion to be created and there's something to be lost from it. Does that make sense?
Yeah.
Okay, yeah.
Is there some like geometric intuition behind the reasons why cross products and determinants have this relationship?
Why what now?
Is there a like geometric intuition between why cross products and determinants have this relationship, or is it just for convenience?
Sure. There certainly is a connection between this algebra and some geometry, and we're going to see a bunch of that as we go through the rest of this section. But in terms of an explanation, in other words, something that would precede this, yeah, I mean, I could take all of the ideas that we're doing here and I could kind of reorder how I present them, and we could take a point of view, completely different point of view on what we take as assumptions and what we take as conclusions, and I could give you a geometric motivation for it. I would rather, though, for this algebra to be motivation for the geometry. So it could be done. I'd rather not. Does that make sense? But certainly I will connect this to some geometry in just a couple minutes. Yeah. Okay. Alrighty. So here's one of the things I really like about this formula. We're trying to learn about the cross product, and what we have here is a formula that relates this cross product that we want to learn more about to a dot product that we already have a good geometric understanding of, and a determinant which we already have a good geometric understanding of. Right? So this triple product formula it's a foot in the door. It's a way to relate things that I'm trying to understand to things that I already do, and that's very often useful in various ways. Okay, let me show you a good first example of that. I'm going to remind you I've already absolved you of all responsibilities for the proofs. So you don't have to read this proof if you don't want to. I'm going to make only the very quickest of references to as quick as I can do anyway. And so you're not responsible for the proofs in this section of the book, right? Outside of this section, no comment, right? You're responsible for everything outside of this section. But the proofs in this section we're going to, in the interest of time, just not cover. But that said, let's look at this result. The result says that a cross product is always perpendicular or orthogonal. I mean, interpret appropriately depending on whether or not these things are zero, right? To both of the two input vectors. Really important fact to know. One of the most useful facts about cross products is they're always perpendicular, both of the input vectors. Now, there's different ways that you could do this, and one, certainly, perpendicularity is confirmed by taking a dot product and just making sure you get zero. Right? So there is an algebraic argument that you can do there. It's just that, okay, you write down the algebra and you get a bunch of terms and they disappear, and that proves it, but there's no geometric satisfaction. Again, as I like to say sometimes, that addresses the fact that this is true, but it doesn't help you get a sense for why it should be true. Right? And I always like to get that kind of satisfaction. So let me try to give you a different point of view on this orthogonality. And for example, how do I know that A is orthogonal to the cross product? How do I know that this dot product is zero? Well, using the theorem we just talked about, the triple product formula, the dot product that we're interested in is a triple product, which therefore is a determinant. And don't forget, determinants tell you volumes. So I've got a little parallelepiped here defined by three vectors, two of which are the same. So if you've got three vectors making a parallelepiped of some sort, but of those three vectors, if two of them are the same vector, right? I guess it'd be more like this. Two of them are the same vector, well, then it's not much of a parallelepiped, is it? It's flat. I like to think of this as a cardboard box smushed for recycling. right? It's just flat. It has no volume, which means the determinant is 0, which means that this dot product is 0, which means orthogonal. So now, this is kind of a different way of coming to the same conclusion, but notice the triple product allows us to relate cross products that we're trying to learn about to dot products and determinants that we already have an understanding about. Notice we used our interpretation of dot product here as telling us about orthogonality, and we used our interpretation of determinant here as telling us about volume. Right? So the triple product formula, as promised, allows us a geometric point of view on something that otherwise would just be kind of algebraic, kind of just nonsense. So anyway, all right. I guess I accidentally did the whole proof. So again, y'all are not responsible for these proofs, and I'm going to literally now stop talking about the proofs. But we do need to enumerate the theorems. Another cool fact about triple products: they cycle. Recall what we talked about cycling previously. Cycling is the process by which you kind of move everything over by one spot, and then one falls off the edge, you bring it around over to back where you began. Right? Cycling preserves the triple product. So these three triple products, all the same. Is that cool? Weird, but it's true. Now again, I think it's a healthy exercise. Good mathematical weightlifting. If you want to get a better sense for triple products and determinants and stuff like that, take a look at these proofs. Think through the sort of the bullet points that I've listed here, and it's a good exercise, and it'll help you get a better sense of these things. But it's not required. You don't have to, and we're not going to spend class time on it. Okay, triple products cycle. All right. This is a weird one. It's a beautiful proof. Very cool. The magnitude of a cross product, which, by the way, looking at a picture down here, there it is. That length, the magnitude of that cross product, is equal to the area of the resulting parallelogram. Right? So if you've got two vectors A and B, they make a parallelogram, they make a cross product, that magnitude equals this area. Really weird result. Very cool argument. Again, I wish we had time. I encourage you to take a look. You're not required, but do make sure to know this result. Okay. Oh, real quick, a notational observation. This notation here, which, by the way, is morally the same as this notation here. When you see two parallel lines followed by a list of vectors, it just means the parallel of whatever defined by those vectors. So here I have two vectors listed. This means the parallelogram defined by A and B, and that's what we're looking at a picture of down here, this yellow parallelogram, right? This notation down here, two parallel lines followed by three vectors, means this entire parallelepiped, again, the vectors cross product and A and B define this parallelepiped. Okay, that's just a notational thing. I saw it once somewhere. I would guess either that or I made it up, but I'm pretty sure I saw it somewhere. But either way, I like it and I'm popularizing it. Okay, everybody good? Yep.
Is area referring to like the area of the base of the
The parallelogram, right? The parallelogram itself is this what I have highlighted in yellow.
Oh, okay, gotcha.
Yeah. Which happens to be a base of the parallelepiped, but we don't need to reference the parallelepiped. Yeah. All right. Okay, moving along. Another cool result, good to know. When a cross product is 0, that tells you that list is linearly dependent. Which, by the way, kind of smacks of a fact previously y'all seen long ago about what happens when a dot product is 0, right? That tells you something about that pair of vectors. Here, when the cross product is 0, that gives you a different bit of information about those vectors. Okay. All right, again, there's a proof. Again, take a look. Again, you're not responsible. Another cool fact. This list, 2 vectors followed by their cross product. Cross product in the same order as you list the first 2 of those vectors. Never in left-hand order. And I would say always in right-hand order, and casually, that's how people tend to think about this. They think it's always in right-hand order, and most of the time it's in right-hand order, but technically one of these vectors could be the 0 vector or something like that, and technically it's not right-hand order. But the point is, it's never left-hand order. Again, proof. Again, you're not responsible. Again, I encourage you to look at it anyway. Okay. All right. Oh, another little cool fact I like to throw out when I talk about this theorem. If you look at this trio of vectors here, and if you ask what is the span of this trio of vectors, what's the dimension of the span? Now you see 3 vectors. It could be that these 3 vectors span a 3-dimensional span. It could be that one of the vectors is like 0 or something, or some things are parallel or whatever, right? Various different possibilities. What's weird is that the span of this trio will never be 2-dimensional. It could be 3-dimensional, it could be 1-dimensional, it could be 0-dimensional. Never 2. And that's a fun little exercise. I encourage you to think back to some, your linear algebra days, and combine with what we've talked about the cross product here. And it's not that much trouble, but it's anyway, it's worth thinking about. Okay, fun fact. Okay, so all together now we have what I'm going to call a purely geometric description of the cross product. Reminder: we defined the cross product with a formula, purely algebraic description. Alternatively, though, if you want to talk about the cross product, it's fair to just define even the cross product to be the unique vector that satisfies all 3 of these conditions. You give me any 2 vectors A and B, there will always be exactly 1 vector that satisfies all 3 of these conditions. And notice they're all geometric. They're all about orthogonality, or area, or handedness, order. Again, all those are geometric ideas. Yeah.
Can you explain again why the second bit is true?
Oh, the why on that is a long conversation. This is one of the theorems that we just talked about. So the why that theorem works is that's more time than we have. It's one of those things where, again, tough decisions, and I've kind of eliminated that proof from the course. If you want to hear that proof, I'll be very happy to talk to you. Hang out after class. I'll walk you through. Yeah. Yep.
If we were to do a proof that involved proving that something is the cross product of another thing, and you wanted to use those 3 points to kind of construct that proof, is there a specific notation for how you would say it has to satisfy these 3 things, and then prove each one or something like that?
Oh, you just say it in whatever seems to be the most succinct. Yeah, there's no specialized notation for it. You just say, well, this vector C, notice it satisfies these 3 conditions, therefore it's a cross product. Yeah, totally. Okay. All right, another cool fact. Now, people see the notation for cross product, and it kind of looks like a times, which looks like a multiplication, and everyone thinks back to elementary school, and they remember that multiplication is commutative. X times y is the same as y times x, after all, right? 3 times 7 is 7 times 3. Who cares about the order? And it's tempting to just kind of get too comfortable with this idea of commutativity. Now, y'all have previously seen that matrix multiplication, not commutative, right, from linear algebra class. Here's another one. Cross product is not commutative. Right? There's a minus sign there. So just do be careful while you're doing algebra with cross products. Certain rules do work. Other rules that you got accustomed to in elementary school don't work. And you don't want to accidentally step on a landmine by forgetting that minus sign. So careful. All right. Yeah, there we go. Okay, now a couple of facts that the book doesn't go through, but I wish they would. I like to point out, and I made this observation on the first day of class, but let me sort of be explicit about it here. Cross product, if you fix a vector that you're crossing with, cross product can be thought of as a function. Right? Cross product with a fixed vector A is a function. You give me an x, I can cross it with that fixed vector A, out comes a result. Right? So that's a function. And that function is linear. Now, you can see that in action down here. Here's crossing with A. Right? And so keep in mind, crossing with A, that's what T is. And notice then this equation that I've written down here really is just very literally a statement about linearity. So in particular, notice that a sum of scalar multiples before you plug into the function t gives you a sum of scalar multiples after you've plugged into the function t. So you can do the linear combination before or after and get the same thing either way. And again, that's what linearity is. So neat fact, worthy of mention in my opinion, and good thing to know. By the way, likewise, if you put the cross on the other side, you'll notice here the crossing with the vector A is on the right instead of the left. That too is a function, and that too is linear. And again, nice exercise. Think it through. The notation's a little bit less convenient here, but morally equivalent fact you can prove. Yeah.
So in part 1, are they indicating that the x vector is a list of vectors? Or
No.
So using like the standard basis.
It's a vector. Now, you can think of a vector in different ways. The best way to think about a vector is that it is a thing on its own called a vector. Right? Now, if you want to write it out in coordinates, then yeah, I could think of this vector x here as having coordinates like x, y, z, something like that. But you don't necessarily have to. Notice in this notation here, I didn't make any reference to any of the coordinates, right? But you could if you wanted to. Does that make sense?
Yeah, but like, is the x1 vector then? Is that just with like the standard basis?
This is just another vector.
Okay.
Yeah, the standard basis vectors we always use e.
Okay.
Yeah, that's so e sub index and then with a little vector arrow over it. That means standard basis vector. Does that make sense? Mm-hmm. Okay. Cool. All right. Oh yeah.
Why are there x1 and x2? Is that like
Oh.
are there more than that, or?
Well, I'm just writing down the definition of linearity, and if we go back a few pages to where we defined linearity, oh gosh, that's further back than I thought. Here it is. Nope, almost. Here we go. Linearity. It involves statements about linear combinations of a pair of vectors. And yeah, sure, you can write it with respect to, you could have a longer list, or you could separate out sort of the scalar multiplicativity or the additivity. There's a bunch of different ways to write it, but I was just making a reference to this one. Yeah, yes.
That exercise that you just had with the cross products on the most recent slide, that was like the same as we were supposed to do on that homework problem, correct?
That sounds familiar.
Like the additional.
Yeah, I don't remember. Maybe I just don't remember. I'm sorry.
No.
Yeah, I can look at it after class if you'd like, but I don't remember. Let's see here. Where was I? Oh, I got it too far ahead. Okay, yeah, here we go. Okay, so real quick, another landmine to be wary of. We're accustomed to taking parentheses and kind of moving them around willy-nilly. You can't do that with cross products. It's not only is it not commutative, it's also not associative. So again, heads up, be careful. Real quick reference to some applications. I don't want to get off into physics, but I do want y'all to know that there are applications out there. A lot of people mistakenly think of the cross product as being just this, mathematicians made something up for no particular reason, right? But it comes up really naturally in physics. Torque, which is, as I have written here, it's a measure of how hard you're turning something, right? If you have a bolt that's embedded into the something and you want to unscrew it, you could grab it with your fingers. That's not going to give you very much torque. On the other hand, if you get a wrench that is this long, now you have a tremendous amount of torque, right? It's a very useful concept for understanding how things rotate in general. And notice the formula for torque involves a cross product. And again, this isn't a physics class, and I don't want to go off into the physics details, but cross product's very relevant there. Likewise, with magnetic fields, weird thing, if you have a magnetic field like so, and if you have something that's moving, in particular a charged particle that is moving with a given velocity, it seems that this world we live in, we have noticed empirically, and don't ask why, nobody knows why, right? But we have noticed that when there's a magnetic field pointing this way and something moving through it with some velocity, that creates a force. And the formula for the force involves a cross product. And again, totally empirical, right? We just notice that this is how it works. So again, this is a natural construction. It's not a made-up mathematicians having fun construction. Okay. All right. So moving along. Section 1.5. Now we're talking about equations for planes and that sort of thing. So here's a plane. And how would I write the equation for it? Now, what plane is that? I can't just wave my hands and say, well, that one. If I'm going to tell you what the plane is and ask for a precise equation for it, I need to be specific. So let's say that I am given a point that's in that plane and that I am given a normal vector, what we call a normal vector, that being perpendicular to the plane. And I appeal to your geometric intuition. If you know a normal vector and a point in the plane, then that uniquely characterizes the plane. All right, so that said, what's the equation for the plane? Well, now keep in mind what an equation is. An equation is a test, right? So in this case, we're not going to try to generate points in the plane or anything like that. I need to find a way of testing points. So in particular, if somebody comes to me with some point x, and as I have it drawn here, let's suppose that x is in the plane, again as I have it drawn here, how would I confirm that? I mean, geometrically, what's my foot in the door to decide or detect that this point is in the plane? And I make the following appeal, and that is, well, if it's in the plane, then this difference vector is parallel to the plane. And now wait a second, in was given perpendicular to the plane. This difference being parallel to the plane would mean that in and this difference vector would be perpendicular and therefore orthogonal. And so this orthogonality gives us that equation. Right? So, by the way, this fact about dot products, that perpendicularity, this geometric state of perpendicularity can be written down algebraically as a fantastic foot in the door. Right? A fantastic way of taking geometric statements and writing it down as an algebraic statement that we can plug stuff into, and that makes for a great test, aka equation. Okay, so that's where the equation of a plane comes from. Now you can write this in various different ways. You can sort of distribute and move things around. That gives you this form of the equation. I don't really have an honest preference between these. Suit yourself. Arguably this one kind of relates to the picture better. But this one down here, I don't know, aesthetically, I kind of like the way it looks. Feels a little simpler. Probably fewer pencil strokes, if I had to guess. I don't know. It's hard to say. I haven't counted. But for some reason, I find this one simpler. So, yeah.
So just like in order to have a plane, you need a vector on the plane or 2 points, and then a vector perpendicular to the plane.
Yeah, let me quibble with your language just a little bit. You need a point on the plane. And keep in mind, vectors don't have locations. Vectors can't be on or not on anything, right? You have to talk about them as points if you're going to talk about their location. But yeah, you need a point on the plane, and then you need a vector perpendicular to the plane. Yeah.
So you don't actually need, you don't need another point on the plane. You only need one, because that'll be, since it's perpendicular, it'll be anywhere in that direct plane. Yeah, okay.
Okay, yeah, that's right. So you need 1 point on and 1 vector perpendicular. That's enough to create your test, but then what your test does, your test is what you will plug into given unknown points that you're trying to decide.
Yeah, and then if that, when you do the dot product with the perpendicular plane is 0, then it's orthogonal.
That's what allows you to create this thing that may or may not be orthogonal. That's right. Yeah. Cool. Okay, now you can also write this out in coordinates, and sometimes you will either be given coordinates or for whatever reason you might need coordinates. Not hard to persuade yourself. You can just kind of multiply everything out. Now keep in mind, we are given the n, and we were given the x naught. So this thing on the right, the whole right-hand side just turns into some number, d, that you can just compute, because n and x naught we know, right? On the other hand, on the other side of the equation, the whole point to this is we don't know what x is. We want that to remain open. That could be anything, but it's going to have coordinates that we can at least give names to. Let's call them x, y, z. And notice with that said, our normal vector coordinates of our normal vector tell us what the coefficients ought to be in that equation. Or you can turn that around backwards. If you have a coordinate equation like this one, just read off these coefficients, a, b, c, whatever's in front of the x, y, z, that's your normal vector. And that's a pretty cool fact. If you have an equation, at a glance, you can find a good normal vector. Cool fact. All right. Quick example. Suppose you have 3 points given. Notice that 3 points, as long as they don't line up or something unfortunate like that, 3 points will define a plane. Right? There's a unique plane that goes through these 3 points. Question.
Back to that prior, multiplied out definition there.
Yeah.
What is D? Is that just
It's just whatever you get when you dot product these two vectors.
Okay.
Yeah, and they're both given, so you can
want
just.
it to be 0?
No. It could be. It's just whatever it is. So yeah, you got to make sure not to distinguish, make sure to distinguish these two equations from each other. Here, there's a 0 on the right-hand side. That's because, in some sense, the x naught term is over here, right? But if you kind of multiply out and shuffle terms around, this goes over to there. So in one of these equations, you have equals 0. In the other equation, you don't. Does that make sense? Yeah. You happy?
Yeah.
Okay. Just checking. Yeah. Yes.
Are those? Is that like multiplying or is that a dot product?
I'm sorry. Where?
Right there where you just were.
Right here?
Yeah.
Yeah, that's a dot product.
Okay.
Yeah, because that's the only. I mean, there is no such thing as just multiply two vectors. That's not a thing. Yeah. Right. All right. Okay. So 3 points given. That defines a plane. How do we find the equation of the plane? There's a puzzle aspect defining equations of planes. This is not an algorithm to be memorized, right? There's a bazillion versions of this example where you're given either a point in the plane or a couple of points in the plane, or maybe a vector parallel to the plane, or maybe two planes that are perpendicular to the plane you're trying to find, or a line whose intersection with another plane has the. I mean, you can see there's countless versions of this kind of thing. So don't think of this as an algorithm, right? Think of this as an example of a kind of puzzle, a category of puzzle, and I'm going to show you kind of a strategy for how to solve the puzzle, right? So we are given points in the plane. We want the equation of the plane. And the big idea is if you're given this stuff, figuratively, and you want to find this, figuratively, kind of work forward from what you're given, and then also kind of try to reverse engineer and work backwards from what you're trying to get to. And in so doing, you might just turn that harder problem into, well, a really easy problem of I just need to connect a couple of dots. And you can turn harder problems into easier problems. So that's what we're going to do here. What can I do with this trio of points? I mean, not much, right? And so, being as it is a short list of things, one of the very few things I can do is I can pairwise subtract to generate now some vectors parallel to the plane. Right? Now, I don't know where that's going for me, but I've reasoned, if you will, forward from my givens a little bit. All right, now let's go backwards from what I'm looking for. I'm looking for the equation of the plane. What would allow me to write down the equation of the plane? Well, a normal vector. If I knew a normal vector, I could use any one of these green points as my x naught, whatever. And that would allow me to write down the equation of the plane. So we worked forward from our givens. We've kind of worked backwards a little bit from our goal. And now, don't view this as I have 3 points and I want an equation. View this as I have two vectors parallel to the plane and I want to find one vector perpendicular to the plane. How are we going to take two parallel and generate one perpendicular? And, well, the cross product is the perfect tool for doing that. Yeah?
Can we interpret the two parallel lines as like span in this case?
You could say that the plane is spanned by these two orange vectors. Sure.
Okay.
Yeah, that's true. We don't actually need that fact, but that is true. Yeah.
What is it? What are you trying to represent in that statement?
In which statement?
With the parallel lines.
This right here?
Yeah.
Just literally that when I take these three green points, when I pairwise subtract to make vectors, that those vectors are literally parallel to the plane. Yeah.
Okay.
Yeah. Yes.
Is there any specific reason that you chose A as your bird times when you were doing C minus A, B minus A?
No, that's a great question. It doesn't matter. Now, you can get yourself into trouble if you get too creative, like if you do A minus C and then C minus B. Now, that's actually fine, but then you think, oh, well, then I could do B minus A and A minus C, or I could do, oh, how about C minus A and A minus C? And that one doesn't work, right? So I like to have a choice that I know works, right? And then deviate from that only if there's something to be gained, right? And so, frankly, not much to be gained by doing something other than this choice. Yeah. Now, on the other hand, if you want to subtract B from both of A and C, yeah, that's morally equivalent, right? But pick one to subtract from the other two, and then you're safe. Yeah. All right. Yes?
Do you have to define the vectors before you cross them to get your normalized vector?
I don't know what you mean.
So the steps are that you would find two vectors like AC and AB on the plane, and then you would cross them to get your normal vector?
Yeah, that's right. Now, and again, I know what you mean. I like to call this B minus A and this C minus A, because again, the algebra is relevant and that's handy. But yeah, you subtract the vectors as written here, and then cross them.
And that those two steps have always been.
Well, that's how you solve this particular puzzle. Yeah, that's right. That's right. And again, the big picture here is not how do we solve this particular puzzle, but how do we solve puzzles in general, right? Yeah. Okay. Yes.
Can you explain why the cross product of those two vectors is therefore parallel to n, and why just like one of them wouldn't be?
I don't understand. I'm sorry.
Like, would just one vector also be parallel to n? Like
Oh, no.
C minus.
Oh, no, yeah, because you can just look at the picture here. Let's see here. If I were to just look at just, I think I heard you say C minus A, that's parallel to the plane.
Oh, I meant perpendicular to n, sorry.
Yeah, it is perpendicular to n. Yeah, it's perpendicular to n, which is part of why I want it to be part of the cross product.
So you have to use, I'm just wondering why you have
Yeah.
to use a cross product, why you couldn't just use like one of them? Is that just to make sure that both?
I just don't know what you mean by using one of them. So I have this green vector, right, and I want to make this orange vector. How are you? If you have only this one vector, I guess I'm not clear on.
I see what you're saying.
Does that make sense? Yeah. So you need. That's what the beautiful thing about the cross product is. It allows you to take things that are parallel to a plane, and by crossing, you create this thing that's perpendicular, right? But so that's a wonderful trick to. Oh my gosh, we've got something perpendicular to our plane, but the cross product is particular, and it requires two input vectors. Yeah. Okay. All right. We are out of time, so we'll draw the line right there for today, and we will pick up here on Friday. Okay. See y'all later. Have a good one.